welcome. We're so glad you're here tonight. This is our this is the third year of our evening science and engineering lecture series here at Anderson University. This is the first one for this season, so we're awfully excited about it. Tonight, we'll hear from Dr. Josiah Kunz. He's an assistant professor here at AU. This is his first year with us. Recently received his PhD studying from the Illinois Institute of Technology. Studied accelerator physics. He did computations on Boson accelerators. Something like that. So tonight, though, he will be speaking to us on the Higgs boson. And I guess it's not the God. So we're going to...
Thank you, Dr. Wallace. Yes, as you mentioned, my name is Josiah Kunz, and I will be talking about the Higgs boson. So let's get started. First, I'm going to talk a little bit about who I am, since I am quite new here. Next, we'll talk about the phenomenon of the discovery of the Higgs, not the actual machinery, but more the cultural phenomenon. Next, we'll talk a little bit about particles and fields and what I really mean by each of those. Don't worry, there won't be any mathematics. I'll try to do it purely conceptually. Finally, I will get to what is the Higgs exactly. And then I'll wrap it up with some frequently asked questions. Hopefully these questions will inspire you to ask your own questions afterwards. So let's get started. First of all, who am I? Well, like Dr. Wallace said, I am from Illinois. I'm about, if anybody knows Dr. File here, I'm about an hour to 2 hours away from his hometown. So we live in central Illinois or southern Illinois, not Chicago. But I did get my PhD from Chicago at Illinois Institute of Technology. And I got it in computational and accelerator physics. So computational physics is physics that uses computers, right? So oftentimes, as long as you know the concept, the mathematics are very cumbersome because they're so intense. Not that we can't do them, but it's just much, much more efficient to do them with computers. That's why I tell my Physics 1 students, you should know the concepts and the math will come later, because if you get high enough, you can sort of cheat that. So the concept in my case was accelerators, that is particle accelerators. And I'll talk about what I mean by a particle accelerator in just a bit. But this is a physical picture of one, in case you were curious. I am married to my wife Meredith, who's in the audience now. We have 2 American Eskimo dogs. On the left is Oliver, and on the right is Olivia. And they're about a year old each, so they're quite a handful, but we love them very much. I also develop independent video games as sort of a hobby. I don't do this professionally, but I do hope to offer a course at Anderson within the next couple of years about developing independent video games. Okay, let's move on to the discovery of the Higgs. On July 4th, 2012, physicists in Europe announced the discovery of the Higgs boson. And so the media really had an explosion about this. So you can see, oh, eureka, this is very good. We've been searching for this for 50 years and it cost a bunch of money. The Higgs boson could make light speed travel possible. That's certainly exciting. The Higgs boson is the very essence of what we are. It tells us something about ourselves. That's great. So what I took in 2012 when I first heard about this, what I took away from this was that the Higgs boson gives particles mass. And I didn't really know what that meant. Is it a particle? How can a particle give another particle mass? That's really not a very good definition, not a very clear definition in my mind. So we'll unwrap that, but that's usually the line you hear. The Higgs gives particles mass. And that's a little confusing, but it was discovered with the Large Hadron Collider, or LHC for short. This is a particle accelerator in Europe, and it has 2 main detectors. One detector is ATLAS, and the other one is CMS. And the CMS is actually shown on the right here with Peter Higgs himself for scale. And I'm not sure if this is an electrical engineering nightmare or a mecca, because it seems like it's very complicated and very expensive, and I feel like if I got my hands on it, I would just break it all. But it's certainly impressive no matter what you think of it. And it costs quite a bit of money. We'll get into the specs later. But it's certainly an impressive detector, and they had 2 of these. Here's a bit of the data. It's not all the data, but it's the data you might see typically of data from the CMS. And I don't want you to have to read all this. I'll explain it to you. The main point here is the black points here are actual data points, right? We've all done labs, and we've gotten data points, and they don't quite fit this line, but they're pretty close, right? So the dashed line here is the theoretical fit without the Higgs boson, and the red line is with the Higgs boson, right? It's the best fit. The yellow and green, okay, what's that? Plus or minus 1 sigma, plus or minus 2 sigma. Well, that tells us how much statistical noise there was. So if you're within this green band, that's telling you, well, that's fine. It's just a little fluctuation of the data, right? We can excuse that away. Maybe there were some errors. You can see most of the error bars are within the green band. That just tells us it's coincidence. But this bump here, this big bump right here, which has been blown up, that's nowhere near the green band. That's certainly not a coincidence. That means there's something there, right? It's not statistical noise. And that's eventually what they ended up calling the Higgs boson. And as I said, this wasn't the only data, but this is perhaps the most famous and most convincing. On the x-axis, you'll see we have an energy scale. You don't need to know what GeV is. It's giga electron volts. But we found it at about 125 GeV is what they settled on. The Tevatron in Fermilab in Chicago was also a particle accelerator, very near to where I went to grad school. And it shut down in 2011. That's 1 year before they discovered the Higgs, which is unfortunate. Unfortunate for them, fortunate for the rest of the world. And they predicted it between 115 and 135 GeV, so they were quite close. Right? This cost a lot of money to narrow it down to that window. And like I said, 50 years. So that was actually a very strong contribution. But we actually nailed it down at 125, so that's a very good thing. Okay, so I've been talking a lot about particle accelerators. That's how we discovered the Higgs. But what is a particle accelerator? What do I mean? Well, of course, it accelerates particles. What do I mean by that? By particles, I usually mean protons and electrons. You can do other particles, but these are the most basic. And the Large Hadron Collider in Europe accelerates protons. To the right, I have another picture of it. It kind of looks like the other one. And we'll see physically, it's this big metal tube inside of this big tunnel. And the reason it's metal is because you really need good shielding. And it's also underground because it's so large that it doesn't want to obstruct traffic or farmland or any other object above land. I also have a little cartoonish cross section. And you can see a lot of things in here. I don't want you to nitpick it apart, but the main thing here is that there are magnets in here. And these magnets keep the protons in a very tight beam. So if you think of a laser beam, it's very compact and it's very bright. That's what particle accelerators do. They take a big range of protons, like you might see on the left here, and they condense it down to this very intense laser beam of protons at very high energies. You can also do this with lower energy accelerators. So I've studied this a little bit in grad school just out of curiosity. But these smaller accelerators like this one, it's called a cyclotron, and it's about the size of this room. And they're in pretty common use, especially in medical facilities. I believe Cincinnati Children's Hospital had one of these for a time. I think they still have one. Because proton cancer therapy has been shown to be very effective, especially in children with cancer. So essentially, you accelerate a beam of protons, like a laser beam of protons, and you feed it through this tube, through the gantry, and down to the patient. And here's the patient to scale of the cyclotron and the whole shebang. And I found that very fascinating. But these are typically lower energy than the big ones, right? And I really want to talk, because the Higgs was discovered with the big one, I want to talk about the Large Hadron Collider, right? This is a very, very large particle accelerator. As you can see, it's on the border of France and Switzerland in Europe. It's about 17 miles around. You can also see where CMS and Atlas are. Those are the two detectors, the two main detectors. And essentially what you do is you get protons on one side and antiprotons on the other side. That's antimatter. And you accelerate the protons maybe counterclockwise and the antiprotons clockwise. And they do that for many, many loops until they get to such a high energy we can actually smash them together. And once we smash them together at the detector, so the detector can actually detect things. And we get this large explosion, very massive, very much energy. And that's where all the data comes from. So this Large Hadron Collider can accelerate protons up to 10 tera electron volts. Sort of for scale, visible light is about at 3 electron volts. So that's about a trillion times more than visible light. So it's quite powerful, but it's also safer than you would think. So it's actually funny because they had, I'll tell you a little story about the LHC. So they had to shut this down before, I think it was in 2010 or 2011, because there were birds building nests in some of the cooling devices. And people actually came up with this story that people from the future sent the birds back in order to stop us from discovering the Higgs, because it would create some type of catastrophic event. No one believed them. They cleared the birds and they went on. And so far, it's worked out, but maybe we'll see. So anyway, let's move on to something a little more conceptual. That's particles and fields. Okay, I find this absolutely necessary when talking about the Higgs. We need to understand what I mean by fields and what fields are. Well, when I say a particle, I really mean a field. All particles are actually fields. And I know that's a little hard to understand, so I have a little cartoon that I've prepared. So here I've represented an electron very simply, right? An electron, in the simplest terms, is nothing but an electric field in blue. And because an electron has mass, it's also a Higgs field in red. So we can see these two fields are propagating side by side. And that's the essence of what an electron is. Right, the electric field, it's invisible, right? We don't feel it, but other charges do, and it extends through the whole universe. Of course, the Higgs field is a sharp point because you don't feel that an electron is solid until you bump into it, right? So let's dive a little bit further into this. You might have heard, especially about light, but also about electrons, that these are both particles and waves. We can think of them about both a particle and a wave. And now I'm telling you that they're all fields. But I have a good explanation for this that I hope sheds some light on this. So you can see if we talk about the electron here, right, the electron, specifically the electric field here, it looks like the electron is somewhere between x equals 3 and x equals 7. So it's sort of out there. So it's sort of smeared over this distance. And so that's what we call the wave-like nature of an electron. We can also see that if we talk about the electron here, it looks like it's right at x equals 5. Right? It has a little wiggle room. If you think of this as a very tiny ping pong ball, it's a ping pong ball located at x equals 5 plus or minus some radius. Right? We call that the classical electron radius. But here's sort of the two ways to think about this. And they're all a field. No matter if you call it a particle or a wave, it's all really a field. So when I say particle, I mean it's a concentration of a field, right? Sometimes we also call that a strong excitation. But that's, it's more or less just a very strong concentration of a field, like here, right? It's a very intense field. So we call it a particle. On the other hand, when we have a weak excitation, right, it's still there. It's a non-zero field, but it's certainly weaker. Sometimes we refer to that as a wave, but they're really the same thing. They're both just fields. And I want you to understand that. So when we talk about the Higgs particle, we can synonymously sometimes say the Higgs field. And I'll get into that right now. So let's talk about what the Higgs is exactly. First of all, I'd like to credit Nigel Holmes, who is a very talented illustrator. He did all the illustrations for this. I'm sure if you Google his name along with Higgs, you'll get to see the little booklet that he made. But when we talk about the Higgs particle, we really mean the Higgs field, right? It's far easier to think of this in terms of the Higgs field. So we can think of this just like Earth's magnetic field, right? There's a magnetic field on Earth. If we had a compass, it would point to north because of the magnetic field. And we can feel this field, even though it's invisible, we can detect it at every point on Earth. So in the same way, Earth has a gravitational field. These are both present through the entire universe. And so is the Higgs field. It might be invisible, but we can detect it. We did detect it. And we can find that it's actually there. So most people learn best through analogy. So to describe the Higgs field, I will also use an analogy. And my analogy will be a field of snow. So it's kind of a pun, a physical field of snow versus the Higgs field. But regardless, our snow field will be analogous to our Higgs field. So we have a few types of things in this snow field that I'm going to relate to real life. So the first thing we have is a skier. So a skier meets very little resistance as they ski along the snow, right? They have to put in a little bit of energy, but they can go a long way, and they can do this fairly easily. On the other hand, if we have a woman in snowshoes, she sort of has to trudge along. She has to fight the snow a little bit harder in order to get anywhere, right? She has to put energy into overcoming the snow in order to get anywhere. The last thing I want to mention is a bird, right? The bird does not have to fight the snow to get anywhere. It just flies over top, seemingly effortlessly. And this is actually the fastest mode of travel in the snow. Right, the bird is hardly even aware of the snow's existence. So, like I said, the Higgs field is exactly like our snow field. And I'll explain what each object is in the snow field. So the skier is like an electron, right? Electrons have a very, very tiny mass. Non-zero, but tiny mass. So it doesn't take much energy to get them to move very fast, right? That's why we have lights in here. Why don't we accelerate protons for electricity? Well, because protons are heavier and they're not as readily available. Electrons are very light, so we can put energy into them and have them circulate the entire room for, not for free, but for very little energy. Just like the skier skis on the snow, not for free, but for very little energy. You might have already guessed that the woman in snowshoes, that's more like protons and neutrons, right? We can still move them. It's still possible. We just have to put a little bit more energy into them. In this case, the Higgs field is really fighting them. They have to fight the Higgs field in order to get anywhere. The coupling between protons and the Higgs field is stronger than between electrons and the Higgs field. The last player on our snow field is the bird. So the bird is like light in this case. Light does not have mass. It is massless. So it moves as fast as possible. Always, 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 light will move at the fastest possible speed. That's why you might have heard that it's impossible to travel faster than light, because light doesn't have any mass. Light does not interact with the Higgs field, right? It doesn't have to fight the Higgs field to get anywhere. That's why you can shine the light from up there. It can come to my face for free. We don't have to put any extra energy into it once we have that light. So there are other particles, more exotic particles that may interest you, it may not. They have a very heavy mass. These are more like a man walking in very heavy boots. They really have to fight. We really have to put energy into them to overcome the coupling to the Higgs field, or in this case, the snow. And of course, these particles interact very heavily with the Higgs field. So this coupling to the Higgs field, that's what we call mass, right? That's how strongly the particles couple to the Higgs field. It's a coupling constant, really. Very similar to how charge is a coupling constant to the electric field. So 50 years ago, physicists didn't really know why some particles had mass, some didn't. Some were very heavy, some were very light. Why aren't they all the same? Right? Why isn't there some symmetry in there? The proton and the electron have the same electric charge. Why don't they have the same mass? Well, a man by the name of Peter Higgs theorized 50 years ago, maybe 60 years ago now, this sort of Higgs field and its corresponding Higgs boson. And he didn't just do this conceptually, right? Anybody can do this conceptually. He had to show the math that it did work and it was consistent with what we know in experiment. So he theorized this Higgs field and its corresponding Higgs boson, of course. There were other theories at the time, right? Higgs wasn't the only one with a theory. And often this happens in particle physics where you have multiple theories and you have to devise an experiment to say, this one's right and these two are wrong. And it took us 50 years to do that. And I don't want to detract from Peter Higgs. I don't want to say he was lucky. He got it right. He's very smart, and he won a Nobel Prize for it, rightfully so. Okay, so in our analogy, the Higgs boson is an excitation of the Higgs field. Right? I talked about excitations earlier, and I'll just revisit them for a second because I believe it's so important to distinguish what we call a particle and what we call a field are actually the same thing. So as I said before, all particles are actually fields. And a good way to visualize this is to have an ocean, right? An ocean is like our field, and if you get an excitation of that ocean, what you get is a wave. So that's a good visual representation of what I mean by an excitation of a field. So for years, physicists have looked for this very elusive, very mysterious little snowflake that is the Higgs boson, and we finally found it. But the important thing is, if you come away with only one thing, it's that the Higgs field, which is the same as the Higgs boson, explains why particles have mass, right? Mass is just a coupling constant to the Higgs field. Okay, so let's move on to some frequently asked questions. Question number 1, why is it called the God particle? Well, my title should tell you that it's generally not. What do I mean by that? Well, the God particle was originally coined by Leon Lederman, who's a physicist, in his book, The God Particle. And he said he coined that phrase because the Higgs boson is so elusive and mysterious, sort of like God is, right? We all don't always know the will of God. He's a little bit mysterious in that sense, but he's also very important, right? God is central to Christianity, and some people believe the Higgs is central to the Standard Model and how particles really interact with one another. So that's the comparison. Unfortunately, the phrase is taken by the media a little too wildly, and so you see it all over the place now. Scientists aren't trying to be stepping on the toes of religion, right? The physics community, as far as my understanding goes, as far as my interactions go, nobody acknowledges this term, right? We don't call it the God particle. We call it the Higgs. We don't even call it the Higgs boson. We call it the Higgs because we talk about the Higgs field. So please don't confuse the two. Question number 2, why do we care about the Higgs boson? Is it useful? Well, my answer is not immediately, but that's okay, right? I know of no one scheming to use the Higgs boson in any type of industrial business, at least for the next 20 years, right? It's just not going to happen immediately. But that's really okay. So to understand why it's okay, we need to go back 100 or 150 years to the Thomson model of the atom. So Thomson, before they knew what the atom looked like, Thomson knew that there was a positive and negative charge because experiments have shown that atoms are charged. But Thomson said, okay, it's a plum pudding model, right? There's this big, massive positive charge that's sort of like the pudding, and there's these little electric charges, little negatively electric charged electrons in the pudding, right? And they're all just swimming around. And this is how it is. Of course, experiments showed that that wasn't quite right. This led to the Rutherford model, which says that, no, the positive charge is at the center of the atom, and all the electrons are orbiting it in a circle. And that's a far more accurate picture. We refined it since, but this really led to this refinement of the model. Okay, but who cares what an atom looks like, right? Well, a lot of people care what an atom looks like. It's very useful to know what an atom looks like. And I will give you at least 3 uses that I could think off the top of my head. There are probably more. Just ask a chemist. Number 1, MRIs. MRIs operate on the principle of electron spin, right? The magnets align electron spin, and once the magnets are off, the spins flip, emitting a photon, and that's how you get the imaging. If you don't know that the electrons have spin or are orbiting at all or have energy levels, you can't operate an MRI. You can't even get close to building this machine, which is quite useful medically. I think everyone would agree. Next thing I thought of was nuclear energy, right? If you don't know that there's a nucleus, if you think there's just one big pudding of positive charge, there's no way you can talk about nuclear energy, right? The nucleus is the root word of nuclear energy. So that certainly matters in nuclear theory, which is quite useful also. The third thing is conductivity, and also superconductivity, which will be useful hopefully soon. We'll see if we get it figured out. But if you don't understand band theory, if you don't understand the conduction band of an atom, right, the atomic structure, there's no way you can start to talk about conductivity unless you do it experimentally, which is maybe not a good basis. So my point is that this quote-unquote pure knowledge often benefits future generations in a very real way, right? You can imagine when they were talking about the plum pudding model, maybe, you know, I lived back then and I'm a farmer. Okay, who cares what an atom looks like? It's not going to help me sell grains. It's not going to raise my children. What an atom looks like doesn't matter. And in the same way, we can say, well, what does it matter what the Higgs boson is? What does it matter what gives particles mass? But we see time and time again, you know, this is just one example. There are many examples of this, how this pure knowledge is super beneficial in a very practical sense to future generations. So just because we can't see it doesn't mean it's not beneficial. You know, humans are very, very good at being efficient, right? Nothing goes to waste. If it's useful in the very least, someone will make money on it. And that's a good thing. Question number 3, are there more Higgs? Right? We've discovered one. Are there many more? The answer that I could come up with is maybe. There might be. Right? You see these other particles over here, particularly this one. This one is way above the 2 sigma green area, right? Maybe that's not a coincidence either. Maybe that's something. Some people call them Higglets, right? Little Higgs around this big one. And the answer is people don't know. There are some models that say, yeah, there are more Higgs, and the mathematics works like this. There's some models that say, no, there's only one, and we don't know. We're stuck back in this we don't know scenario because the math works on several different models. We don't know what reality works. But fortunately, the LHC is still running, and it may discover more little Higglets. We'll just have to wait. Question number 4. What was the United States' involvement in the discovery of the Higgs? The answer, of course, is we had a very large contribution. So I know I told you the Large Hadron Collider was in Europe, but just like most major experiments, certainly in particle physics, this was an international collaboration because one country or one even continent alone simply does not have the resources to support an experiment of this magnitude. So let me throw some numbers. The US provided about 2,000 physicists, which was more than any other single country. And furthermore, let's talk about actual manpower on the floor at these 2 main detectors. So as I said, there are 2 main detectors, ATLAS and CMS. About a quarter of the ATLAS collaborators were American, and about a third of the CMS collaborators were American, shown visually on the right also. But what about Americans in key positions, leadership positions? Well, Joe Ancandela from University of California, Santa Barbara, led more than 3,000 physicists just under him at the Large Hadron Collider. And furthermore, he got to make the official announcements of the Higgs to the press, which is sort of every physicist's dream to announce a new particle to the world. And that's a very high honor. So certainly we're seeing Americans in key positions at the LHC also. Okay, what about the detectors? What about the detectors themselves? Not the manpower, but the technology. Well, here's a list of specific things that the U.S. helped with. And I won't go over every one. You can read them if you're really curious. And I'll give you a second to read those. But I want to talk financially about what the U.S.'s involvement was with these two great detectors. So let's go over some specs. Both Atlas and CMS have a resolution of about 100 million pixels, which is quite large. Furthermore, they can take 40 million pictures per second, which again is quite large. So you can imagine they're very complicated machines. We saw one opened up. There are a ton of wires, but they need to be this good in order to discover the Higgs. The United States contributed about $164 million to Atlas, about $167 million to CMS, and about $200 million more to the construction of the LHC as a whole. Now, the total cost of the LHC was about $9 billion. So these may seem like small numbers when compared to that. But on their own, I think that's pretty good. We have about $500 million invested at the LHC as a country, which is, of course, non-trivial. So my next point is, okay, we have a resolution of 100 million pixels, 40 million pictures per second. What was the U.S.'s involvement in computational overload? Right, so the LHC produced a lot of data, especially if it was running 24 hours a day at 40 million pictures every second. So the LHC used data centers from around the world. We have two main ones in the United States. That's Fermilab, which is located in Chicago here, and Brookhaven, which is on the East Coast here. And they forward them to other smaller data centers, but the two main ones were Fermilab and Brookhaven. As a whole, the US provided, again, about a quarter of the computational power to Atlas and 40% computational power to CMS, just processing and analyzing this data and getting it in a human-readable format. And that's quite impressive. That's quite a bit. Which leads me into my next question. Okay, we get it. The United States contributed a lot to the discovery of the Higgs. But why couldn't the US do all of it, right? Why couldn't we discover it with US physicists on US soil in a US-run facility? Well, there are several reasons. Of course, $9 billion being the biggest one. Congress does not want to spend $9 billion in accelerator physics alone. They want to spread that out over all science, which is fair. Also, $9 billion, that's about the cost of 2 aircraft carriers, which seems about right, but it's awfully expensive. Furthermore, you need raw manpower, right? We had one American over 3,000 physicists, and you need all of these physicists to be very talented, right? These can't just be 3,000 of any physicists. They have to be the best in their fields, the best electrical engineers, the best data analysis, the best simulations experts, even the cooling of the beams, the vacuum pumps. These all need to be the very best people working. And furthermore, you need a lot of computational power. I showed you how much computational power the US contributed. It wasn't even half. So we really, any type of effort like this needs international collaboration on the computational power alone, unless Google wants to help us or something, because they have some pretty good machinery there. But even so, I think we could have done it. And that's not just American arrogance talking. I do have data to back it up. Here, it's quite hard to see, but this is the best I could find. We have an aerial picture of Texas. Right up here, you see the Dallas metropolitan area. And down here, you see this ring. And this ring was the site of an accelerator in the past. This was the Superconducting Super Collider. It officially got funded in 1987. Right? This was approved by Reagan in the middle of his second term. And it was finally killed by Congress within 1 year under the Clinton administration in 1993. Please note I am not blaming Bill Clinton himself for this. That's just a good time marker of when things happened. The truth is, mistakes were made on both sides, by the government and the scientific community. You can argue that one side made more mistakes than the other. But in general, there was general distrust between each other. The governments would make random audits and check out the facilities a little too often. And the scientific community kept saying, well, we need just a little bit more money, just a little bit more money. So the whole thing sort of fell through, and it's really sad that happened. There were also some foreign funds that never came that would have really helped out with the funding. But let's not talk about the negatives. Let's talk about the positives. It was planned to be 20 times bigger than any of its predecessors, so it was quite ambitious. At a circumference here of 54 miles. That's 54 miles around. Remember I said the LHC was 17 miles, so this is quite a bit bigger than the LHC. And this was 20, 25 years ago. It had a maximum operating energy of, people estimated 20 tera electron volts. And if you remember, the LHC its maximum is 14. It's not quite up to 14 yet, but this is where we think the technology will be limited. It'll go up to about 14 and stop. So this is quite a bit more, about a third more, or 50% more than the LHC we would have gotten back in the 90s. So that would have been great. The total cost, people don't know because the funding got cut, but people can estimate. That's why I have the little wiggle here. About $11 billion. That's 1990s dollars, so it's actually more now. But you can go figure the cost if you really want to calculate inflation and whatnot. The LHC, remember I said, was about $9 billion. So if I look at the numbers, I think that's really a bargain, right? It's only $2 billion more, but you get 50% more energy. That's a really good deal. But I'm not part of Congress, and it's a very complicated thing. And so that's sort of the super collider that could have been in the United States. But for better, for worse, they decided to shut it down. And the U.S. still had a really good. I told you the Tevatron in Chicago was an accelerator that narrowed down the range of the Higgs. And I think with a little more time, the Tevatron could have actually discovered the Higgs. But this one certainly would have. OK, so let's conclude with what we've learned today. The Higgs boson, like all particles, is actually a field. Right? This is why many quantum mechanics books are retitling themselves as quantum field theory books, because really we're talking about fields. The Higgs field gives mass to some particles, and not to others. Like it doesn't interact with light, whereas the Higgs field interacts with protons and neutrons very heavily. Right? The Higgs field drags them down a lot more. Accelerator physicists in the US still have a very large global presence and on the whole are still very successful. So you can see here the Higgs. This is the standard model. These are all of the fundamental particles as they fit into the standard model. There are some things not in the standard model, like dark matter or like supersymmetric particles. But these are sort of the standard ones that everybody agrees, yeah, this is a safe bet. And you can see the little electron right here. That's probably the most familiar one. And now the Higgs. Now you're familiar with the Higgs. You know what that is. And that's right over here. So the US has also strong presence at Daya Bay in China. Actually, I think they're wrapping up now. They've already made the discovery. But that has to do with neutrinos. And so that's very nice. What you might not see on here that some people might claim is a graviton, right? A gravity particle. And LIGO just discovered gravitational waves. So where there's a wave, there's a particle, of course. So really, the standard model, as far as the US sits, it's looking pretty good for us, right? We've contributed to the main frontiers of research, which is the Higgs, neutrino studies, and not here, gravitational waves. Finally, the superconducting super collider in Texas is the one that got away, and it's sad, but we should really count these things as a species. I'm just glad somebody discovered the Higgs. Yes, it was mostly Americans anyway, but we're really fortunate that we're making progress as a species in physics. So I would like to thank you for coming and listening. Are there any questions? Yes?
That super collider in Texas is still there.
Yes,
Is there any chance to restore it, get it working again, given
Yes. Right. So I would say, well, I mean, I suppose the land is still dug out. They still have the plot there. I don't think any of the machinery would be wise to use that. Partly because it's old and we have better stuff, and partly because people probably don't trust it. And right now, so I worked with muon accelerators, which are smaller for the same energy. And the government just cut funding to that. So particle accelerators, as far as funded by the United States, doesn't look very good. So I would say not anytime in the near future. But my secret hope as a physicist is maybe someday. Yes. Sure.
My understanding from my very small background in physics is that a number of the particles were discovered because there were some unexplained aberrations in theory that we already had in mind. Was that the reason the Higgs was predicted and searched for, because there was some unexplained phenomenon?
Okay, so I have to say a
my
disclaimer. I am an accelerator physicist. I have taken particle physics, graduate level 1 and 2, and I have a passion for it. But my research isn't in particle physics, so I have to disclaimer. But no, I think particles like the neutrino and even the photon, right, light particle, those were discovered to explain something that we couldn't explain otherwise. The Higgs, on the other hand, I don't think there was some aberration other than the existence of mass. And by mass, I don't mean gravitational mass. I mean inertial mass, right? Mass due to forces and collisions. So I suppose it was invented to explain that, and like why electrons are very light and protons are very heavy. So I suppose it was invented to explain that asymmetry, right? There's not a symmetry in the universe. Light particles don't have any mass, electrons do. Why is that? Well, because there's this asymmetry. And how do we explain that away? So in a sense, I would say yes, but not any experimental evidence in the same way that photons or neutrinos were theorized.
All right, let's thank Dr. Kunz once again.